This episode of the HVAC School Podcast is made possible because of the generous support in so many ways from Testo, RectorSeal, and Carrier. And I want to mention I'm going to be at AHR, the AHR conference in Chicago this January, starting on January 22nd, which is a Monday. January 22nd, 2018. I'm going to be at the AHR conference, and for those of you who listen to the podcast and would like to hang out, I'm going to try to grab lunch and dinner with some of you, maybe breakfast, who knows. My brother Nathan's going to be there. Some of you know him from the Facebook group, and we're going to have a great time. Hope to see many of you there. But one way to see me and also see a pretty cool tool is by going to, actually seeing me and seeing a cool tool might be the same thing. Anyway, I digress, is by going to the RectorSeal booth. And so that is booth 2545 at AHR. And from 2 p.m. to 4 p.m. on January 23rd, which is Tuesday, I'm going to be demonstrating the ProFit tool. So we'll probably demonstrate it a couple times. If you have questions for me or anything you want to talk about, you can come by and talk to me there at the RectorSeal booth. But you can also enter to win at the RectorSeal booth for a if I'm not mistaken, and don't quote me on this, but I think they're giving away one of the ProFit flare kits and then also a swedge kit, the new swedge kit that they make. And it's a really, for those of you who don't know what ProFit is a really great flaring and swedging tool that you can use. It just goes onto a drill or an impact. It has a chuck on it. It's made primarily for high RPM drills, so you got to have a good quality drill, but you can make a really, really nice flare and swedge with that tool. The flare kit's already out. Swedge kit will be out very soon. I would also encourage you to go check out the Testo booth, 7365. I'm going to be in and out of that booth as well. They've got a lot of great products, a lot of new products that they're going to be rolling out here very soon. Again, I've told you many times that I like a lot of the Testo products. Two of the products that I use all the time are the Testo 770-3 multimeter. It's the multimeter that I use. So for all the tests in this podcast for voltage and resistance, that's my go-to multimeter that's in my go bag. Of course, I don't go as much as I used to, but a lot of my technicians have also used the 770-3 and like it a lot. And then also the Testo 550 manifold is sort of our go-to workhorse manifold that we use throughout my company. It's just a great, reliable manifold. When it comes to the digital manifold, it's very, very accurate. It uses thermistor probes instead of thermocouple probes, which means that they're more accurate on the temperature reading. It just does a great job, and it connects to the app, which a lot of my technicians use, especially for like measuring pressure drop when they're doing a standing nitrogen test. It's really good for that. Just a lot of really, really great products over at Testo. So you can go see them at 7365, and you might see me there as well. Look forward to meeting you at AHR. That is Chicago, McCormick Place, starting on January 22nd. That's a Monday. And I'm going to be specifically at the RectorSeal booth on January 23rd, which is Tuesday, from 2 p.m. to 4 p.m. Hope to see you there.
Meet Zoomlock, the 10-second flame-free refrigerant fitting from Parker. Reduce labor costs by 60% with no brazing, no flame, and no fire spotter. Discover how Zoomlock can help you be more efficient and productive. Visit Zoomlock.com for more information.
And now, the man who tries to explain makeup, air, and ventilation to his kids whenever they eat out. Bryan Orr.
Hello. This is Bryan with the HVAC School Podcast. This is the podcast that reminds you of things that you might have forgotten along the way about the HVACR, heating, ventilating, and air conditioning, and refrigeration service arena. Or it reminds you of some things that you may not have known in the first place. And today on the podcast, we're talking about voltage and resistance. We're going to talk about amperage today. Amperage is going to get left out today. Amperage and wattage, they're sitting on the sideline. We don't need them in the game, but we may call on them shortly. So because this is just me talking, I'm not going to do the typical, intro thing where I intro the host. That would be kind of weird if I introed myself, like read you my credentials. First of all, actually be kind of short. So we'll just skip that. But today we're going to talk about actually using a multimeter and some things that you may notice. Because, it's interesting. If you go in any of the Facebook groups and somebody asks a question about motor load and how it's affected by voltage or just different questions like that, people will just start saying, Ohm's law, it's Ohm's law, you should know Ohm's law. If you don't know Ohm's law, go back to school. But it's interesting because in the real world, very few of us ever work Ohm's law. I mean, how often have you actually sat down and used Ohm's law in a practical way? And so let's use a practical example here. Let's say you take a compressor. and you ohm it out. And so you take, let's say that compressor says that it has, 3 ohms on one of the windings, okay? And if you take Ohm's law, you take 3, hold on, I'm pulling out my handy dandy calculator here. This is pretty complicated math here. So we're actually going to take, because it's E equals I times R, so volts equals amps times resistance. So if the resistance is 3 ohms, we're going to take the volts of the compressor, so that's 240. We're going to divide that by 3, and that's going to give us our amperage, right? Whoa, 80 amps. That's really high. That compressor is going to draw really high amps. The fact is that the compressor does actually draw high amps initially when it starts up. That's what we call locked rotor amps. So we actually had this long conversation on the Facebook group recently. I did a video on it. If you want to find out about that, you can go to Facebook, look up HVAC School in the groups section, and go over there, and you can see that video that I did and some of the heated debate that followed. And it mostly followed because I said you don't always need to ohm out a compressor, but I digress. We're not going to talk about that as much today. We'll touch on it slightly. But if you take that math and you say, okay, well, that compressor is going to draw 80 amps. Well, actually, no, that compressor is not going to draw 80 amps because the real resistance in a motor, I mean, there is resistance that you can measure with the motor de-energized, and that's what we just did. We measured the ohms on the windings de-energized, but as soon as you energize those windings, there's additional resistance that's added because of the expanding and contracting magnetic fields. Now, this is one of my favorite topics to talk about. It's just it's a nerdy thing, but it is practical. So if you listen to past podcasts, you'll hear me talk about inductive reactance, and that's what that is. Inductive reactance is electromagnetic resistance that only occurs when the motor is running. And if you've ever tried to ohm out a motor or a solenoid or any type of electromagnet, any type of inductive load, magnetic load, you will have observed this, that the resistance seems low. Or I mean, when you do the math, when you work Ohm's law, the resistance seems low. But the only way to really get that resistance truly on an electromagnet is to energize it with the design voltage and then measure the amperage, and then you can back into what the total resistance is or what the total impedance is. And so when we say impedance is measured in ohms, and impedance is equal to both the traditional resistance, the resistance that you can measure with no power applied, plus the inductive reactance. So the resistance of the winding plus the inductive reactance, the magnetic resistance. And so let's say that we were to power this compressor up, we would have to take both windings, and then we would take the voltage on each winding, and then we would take the amperage of each winding, and then by that we could calculate the actual impedance. And you also have to take into account the capacitive reactance of the run capacitor. So it's not a calculation that we typically are going to do. We're not really trying to figure out what the impedance is of a compressor regularly. We're just measuring what the resistance of those windings are without it being energized, which you just can't work. Ohm's law just isn't that simple. And then you also have to, whenever you're talking about alternating current, you also have to take into account for power factor. So there's just a lot of different factors there. So Ohm's law, in a practical sense, we don't use it a whole lot, and at least we don't use it for the math. But what we do use it for is we use it to understand the relationships between these three things. Specifically, in Ohm's law, we're talking about the relationships between voltage, between amperage, and between resistance. And when we think of something, let's start with something really simple here. And so we're just kind of backing into this. So we're going to get into how to actually use a meter and what some of this stuff means and how it's practical. But let's talk about something really practical. Like the most simple load that exists would be a light bulb. I mean, that's what we typically think of when we draw our most basic diagrams, when we create really basic projects to show someone how to use a switch and how to wire up a load and how to wire up a power source with a battery. We're always using a light bulb. So we think of a light bulb as being a very, very simple type of a load. But before we even do that, before we even do the light bulb, let me just take a quick breath here. It's nice and calm. I start talking a little fast when I get a little excited talking about this kind of stuff. What is a load in the first place? I mean, what is it really? So I define it generally on the podcast, and a lot of other people will define it this way too. It's the part in an electrical circuit that actually does something. It's the part that does work, right? Well, is that really what's happening? I mean, what is really happening inside of a load? Well, it has electrical resistance. And the result of that electrical resistance, and really, is it the result of the electrical resistance? It isn't even quite that simple, but we'll just say that for the case of simplicity. We'll say the result of that electrical resistance can be electromagnetism. That's pulling in a solenoid. That is creating and expanding and collapsing electromagnetic field. that creates rotational force in the case of a motor. That's a solenoid. That's even a speaker. Like a speaker is an inductive load. It actually sends magnetic impulses that drives and creates air vibrations, drives a diaphragm on a speaker and creates vibrations in the air that we recognize in our eardrums as having meaning, as having sound, to replicate something. So we see electromagnetic loads all the time. They do something. They vibrate a diaphragm in the case of a speaker. They draw on a solenoid in the case of a reversing valve coil, for example, or a contactor solenoid that pulls in those contact points. It spins a motor. You can address some of those. So those are common. But then we also have resistive loads, and resistive loads generally create light and heat, or what we call, we say creates it. It doesn't create anything. In reality, you're just changing energy from one type of energy to another. So the movement of electrons is then being converted into light and heat, something that we can sense. So a load is the part that does that thing. Let's not overthink it here. We can go in an engineer's direction with any of these things and look at them far more technically and far more mathematically. But really the point of this is to say that as far as a technician is concerned, if you work in this field, you care about the relationships between things and understanding how they go together, not so much the ability to always replicate the math. There are some areas where math makes more difference, but in electrical especially, you're not going to do a lot of electrical math as an HVAC technician. It's just not going to happen that often. And if you do need to do it, well, then you just know where to look it up so you can find it. I mean, remember E equals I times R. That's pretty simple. That's Ohm's law. Very basic. But anyway, so I digress. So we think about a light bulb. And you say, okay, a light bulb. What is fixed on a light bulb? And this is where people get the most confused whenever I do these sorts of quizzes or anything like this with light bulbs or heat strips or whatever. I'll say, what is fixed on a light bulb? Well, they'll say, well, the wattage, right? Because the light bulb's rated at 100 watts or 50 watts or 40 watts, 30 watts, whatever. Well, the wattage isn't actually fixed. The wattage is fixed because it has a rated voltage. And so for an average light bulb that we plug into a socket in our house is rated for a specific voltage. So 120 volts in most cases, 110, 115, 120 volts. And so it's at that voltage that light bulb will be a particular wattage. And so there's an assumption made, and the assumption is that the voltage is fixed. Now, if I change the voltage, then that will also change the wattage of the bulb. I mean, it's pretty clear that it will. But when people look at Ohm's law or they look at Watt's law, they get these things convoluted because they think that the wattage is fixed. So they assume that, well, if the wattage is fixed and you change the voltage, well, then the amperage must go up in order to keep the wattage the same. But of course, it doesn't do that. A light bulb it's rated for a particular wattage, but the assumption is made by the light bulb manufacturer that you're going to apply a fixed voltage. And so when you change that voltage, you change the wattage output of the bulb, or in actuality, what the bulb is really doing is outputting lumens. So you could have a bulb that's rated at a specific lumens, which is actually the light output, and you could say, well, it's the lumens that's fixed. Well, no, it's not the lumens that are fixed. The lumens are fixed. It will output this much light if it's provided this particular voltage, and then it will then produce this particular amperage, which results in a specific wattage. So this is all, we have this end output, but there's an assumption, and the assumption is that you are providing the proper potential difference, the proper voltage that the bulb requires. And so you say, okay, well, if the wattage or the lumens aren't really fixed, then what's fixed is the resistance then. The resistance is fixed. And so I should be able to take this bulb and I should be able to ohm it out, and it should give me the resistance of this bulb, and I should be able to work Ohm's law and tell exactly what the amperage will be. And then I can, calculate that with the voltage, and then I should be able to get the wattage, right? And then that will tell me, that's fixed. It's the resistance that's fixed. Well, actually not. And here's why. Because as the filament in a bulb, which the filament's the part that gets hot, the part that lights up on a typical incandescent light bulb, which, again, we're talking incandescence here. We're not talking LEDs. We're not talking fluorescence. Those are different methods of producing light. On an incandescent bulb, as that filament heats, it actually has a higher resistance. So initially, when that bulb, if you were able to measure this on it's very quick, you had a meter that could just catch this right away in the first couple cycles, you would notice that when the filament is cold, it has a lower resistance and therefore draws higher amperage than when that filament heats up. And this is true of most conductors. Now, this isn't a universal rule about all different types of matter or everything, but for most conductors, when a conductor is hot, it has a higher resistance. And when a conductor is cold, it has a lower resistance. Now that may be either counterintuitive or intuitive for you, depending on how far along the path you are with electrical theory or electrical understanding. But here's what you have to recognize, is that the more current that goes through a light bulb filament, the more resistance there is. And the more resistance there is, the less current can go through the light bulb filament. So those two things are kind of, those two ideas are opposed to each other, right? But it self-regulates. So it hits this point of self-regulation where once it hits a certain temperature, then the resistance is increased to a certain point that then regulates it so that it doesn't keep getting hotter and hotter. Actually, I mean, if you think so, I'll give you a second to wrap your head around that. But again, the fact is that when resistance on something is higher, and this is what Ohm's law does tell us, when resistance is higher, amperage or current is lower so long as the voltage stays fixed. And in a typical, commercial residential application, we see the voltage generally in most running operations, it stays fairly fixed, right? You have 120 volts at the outlet. That doesn't fluctuate a whole lot in most cases. And so the voltage is fixed. And so if we increase the resistance, then the amperage decreases. If we decrease the resistance, then the amperage increases. That's what we call an inverse relationship. So it's not, the amperage doesn't go up with the resistance. The amperage goes up when the resistance goes down. The amperage goes down when the resistance goes up. That's known as an inverse relationship. But in a light bulb, what we're saying is that if you were to ohm a light bulb out, you would think that the amperage should be higher and therefore the wattage would be higher. But once you actually apply the rated voltage to it, you find out that the amperage is actually lower. The wattage is actually lower than what you would think just by ohming it out, because as that filament heats, the resistance of the filament increases. Okay, now, you're probably wondering why the heck is this important? Well, it's important because when we throw around a phrase like Ohm's law, or we throw around a phrase like Watt's law, you have to understand what is the constant in this equation, or how do you figure out the variability or the dynamic range in an equation? How do you figure out the change in an equation then? And for most of us in the field, we're not engineers. And so we can understand a concept like Ohm's law, and we can understand it from a broad standpoint, and we can get a good sense of it, and that's good for us to do. It's good for us to understand those relationships. Like, for example, that when electrical resistance decreases, current increases. That's good for us to recognize that, right? Or when voltage increases, if the resistance remains the same, then the amperage increases. But to do the actual math is trickier than we think it is, because even things that we think should be fixed, like, for example, the resistance of something, really never is fixed. I mean, it really never is fixed. Temperature changes affect the resistance of a substance, and when you're dealing with an electromagnetic load, an inductive load, the resistance changes whether or not the load is energized or de-energized. And it also changes with, when you have something like an electric motor, for example, the frequency that motor is allowed to spin, meaning how fast is that rotor, the part that actually turns in a motor, allowed to spin in relationship to the stator, the part that stays stationary. Is it allowed to get close to the synchronous speed, or is it forced to lag because it's put under more load? That affects the resistance in those electrical windings, which results in changes in resistance or changes in impedance of that circuit. And again, just to be clear, when I say impedance is just the inductive reactance in addition to that resistance that you can measure initially with an ohm meter. So why am I telling you all of this? It's important to set the stage for using a multimeter, because the first key to using any tool is knowing its limitations. If you don't know the limitations of your tool, then you're going to be given false confidence, and there's nothing worse for a diagnostician than false confidence. I mean, maybe the other thing would just be complete incompetence, where somebody knows that they don't know and they still just, walk away from it or whatever. I mean, you see technicians do that from time to time, but once you get past that first stage of knowing that you don't know, this next stage is thinking that you know, where technicians think they understand and they think that their tools are providing them with this answer that in fact their tools aren't providing them with. So let's take a common one. We're just going to use some very common scenarios here. I'm not going to get super technical. Like, for example, describing how to read a diagram on a podcast is essentially pointless. But there are some things that relate to how we talk about diagnosis. So the kind of thing that you'll call a buddy or a senior tech and ask them about that we can talk about on a podcast. So let's use a common one. Let's say you're working on a heat pump condenser, and a heat pump condenser. So just for the sake of clarity, it's just a basic single stage, residential, heat pump condenser, you have a couple wires. You have more wires than what you would normally have with a straight cool, where you would normally only see yellow and blue. It's really just, in a straight cool, in a lot of cases, you're just energizing the contactor in a simple straight cool. But on a simple heat pump, you've got red, you've got yellow, you've got blue, you've got white, you've got orange, okay? So you've got multiple conductors there, and they all do different things. They serve different purposes. And then you also have common. I don't know if I said blue already, but you also have common. So a lot of technicians, a lot of newer technicians, they'll call. So they'll call me and they'll say, "Hey, my contactor's not pulling in." All right, well, what are you reading at your contactor? Well, I've got 24 volts. They'll say it just like that. I've got 24 volts. All right. And I've learned over time not to trust that, because they'll just want to be like, "I've got 24 volts and it's not pulling in. What do you think it is?" All right. Where are you reading 24 volts with the two leads of your meter? So senior techs out there, that's the next question. Anytime someone says they've got voltage, I'm doing air quotes here, they've got it, you've got to define what 2 points are they reading between, because on a voltmeter, you're always reading between 2 points. And what I tell, and I've talked about this on a recent podcast, but whenever you're using a voltmeter, you're only going to read voltage if you're reading across 2 points that have a difference in charges. And for them to have a difference in charges, there needs to be a reason for them to have a difference in charges. Just because they both have potential, meaning they both have voltage in reference to ground or neutral, does not mean that there's going to be a difference in charges between the 2 points that you've chosen. So a common one will be, so the technician will say, like I just said, I don't have voltage in my contactor. Okay, well, where are you reading between? Well, I've got nothing in between yellow and red. Okay. Now, most of you know, if you've done this for a while, you know that that's not how you do that. You either read across the contactor coil itself, which is kind of my preferred place to start, or you could read between yellow and blue coming in. That would tell you something, blue being common on the opposite side of the circuit from red. So when you read between yellow and red, what are you really doing? Okay, so think of this as in the terms of a very simple diagram. So you've got 24 volt potential that's between the two secondary legs on the transformer. So, primary is the high voltage coming into the transformer. You have two wires coming in there that energize the primary, and then you have the secondary that's energized. And there's differences in potential between those 2 points on the secondary. So those colors might be red and green. That's a real common one for the secondary on a transformer. And the colors don't matter, but there's a difference in charges between those red and green wires there. And so you make a circuit in between those two wires, and it needs to go, in most cases, you're going to have the hot line, which what we call hot. We'll use red, and if we're looking at a diagram, that's on the left side of a diagram. And then you go to a thermostat, and the thermostat is both a load and a switch, but it's primarily a switch. And so it switches in between that red and the different legs of power. And what we would call the load side of the switch is what comes out of the thermostat. So that yellow wire is what we would call a load side or a switched leg. And so that yellow wire is now energized if that thermostat is closed. And so there's no potential difference between red and yellow if a couple different scenarios happen. You would have no potential between red and yellow if both red and yellow are energized with 24 volts potential in reference to the common side of the circuit. You would have nothing. You would read nothing between those 2 points. You would read nothing between those 2 points if there was no power on the circuit whatsoever, right? You would also read nothing between those 2 points. You could also read nothing between those 2 points if, say, the contactor coil was completely open, or if the common was open, so that there was no circuit all the way through, because then at that point, even though you are reading across an open switch, there would still be no difference in potential, so imagine it this way. Imagine that you have a contactor coil that's fully open. It's cut inside that contactor coil. And so in between the Y terminal on the thermostat and that contactor coil, there's no connection to anything else. Now, again, we're using a theoretical system here. Sometimes you can get bleed through on certain types of controls or whatever. We're talking about a very simple theoretical system here. And so between that Y terminal on the thermostat and that cut contactor coil, if that thermostat is off, so cooling is set to off, now there's no potential in between Y and that cut coil portion, right? And so if I read in between red and that Y, I'm not going to read anything because there's no path to anything. It's a little isolated segment of wire, essentially. It's doing nothing. And so reading between red and yellow at the condenser tells me basically nothing, because if the switch is closed, I'll read nothing. If the switch is open but the circuit isn't intact, I'll read nothing. And if nothing is energized, there's no power on red or yellow, then I'll also read nothing. And so it doesn't give me much good information in comparison to checking between yellow and common, because between yellow and common, that's telling me, do I have 24 volts coming out of that switch, which is the thermostat, between that point and the other side of the load? 24 volts difference in charges between those 2 points. Okay, so that's a common thing that people will get mistaken, is trying to read in between two hot legs or a line and a load side leg across the switch. While that can be valuable in some cases, it's not as valuable because you have to know some other pieces of information in order to know whether or not you have any potential on that circuit at all at that point. All right, so that was kind of a complicated way to go around and tell you that when you're using a voltmeter, you generally want to plant on the low volt. If you're doing low voltage diagnosis, you want to plant one of your leads on the common side and then kind of walk your way through the circuit with the hot lead, and not try to read in between a line and a load side of a switch, and not use ground as a reference point because you don't know how reliable that reference point is. You don't know how well ground is connected back to a transformer or to anything else. Ground isn't what you want to use for diagnosis in almost every circumstance. So, and I've beat that dead horse in the past. So we're moving on from there. But I just wanted to give an example of how technicians can trust a meter to tell themselves, oh, I've got 24 volts, or no, I don't have 24 volts. And what they really need to be thinking about is, where do I have these two meter leads placed? And are they placed in a position that there should be a difference in potential? So now let's answer the question, when do we see a difference in potential between meter leads? And where we start here isn't maybe as simple as a lot of you, because whenever we talk about these sort of more basic things, a lot of senior technicians come out of the woodwork and say, well, it's obvious, just use common sense. I had somebody say this just the other day, just use common sense in a meter. And I'm thinking to myself, using a meter is not common sense. Using a meter is something that you have to be trained how to do. But here's the first question that I want you to answer. All right, when you're looking at diagnosing something specifically with a voltmeter, are you working with dynamic current, or are you not dealing with dynamic current? Are you dealing with just simply potential? Because when you have dynamic current, meaning you actually have current moving, you treat the circuit a little differently than you do when you do not. And let's give an example. So let's say you walk up to a light bulb. We'll just use the light bulb example here. And you walk up to a light bulb and the light bulb is not lit. You put an amp clamp on the light bulb and there is 0 amps. All right. At that point, you know that on that particular circuit, it is not there's no dynamic current. The light bulb's not lit, there's no work is happening, and there's no amperage on the circuit. All right, and there's tons of different examples of this. This is when you go up to a contactor and it is not pulled in, or you walk up to a condenser fan motor and it is not running. These are cases where you have a circuit and that circuit is not doing anything, and not just not doing what it's intended to do, but doesn't appear to be doing anything. And so then you clamp an amp clamp on it. And I said I wasn't going to talk about amperage, but shoot, I did anyway. But you clamp an amp clamp on it and it's not doing anything. So at that point, you either don't have any potential difference in the circuit at all. So that'd be like, my breaker's off, my fuse is blown, something like that. There's, either there's no voltage applied at all, no potential difference, or there's something in the circuit that's broken. The circuit is open, right? So that can be a lot of different reasons. In a motor, that could be a thermal overload. It could be a switch that's open. It could be a safety that's open. It could be a lot of things. But all we know is at this point that there is no dynamic electrons. Dynamic just means moving. The electrons aren't moving. There's no current. We don't have current on this circuit, okay? So that's the first thing you really need to assess when you're looking at a circuit is work being done here actively? Because it does affect how you make decisions about testing. And so let's give an example. Let's say you have a contactor that's not pulling in, right? Well, in most cases, when you have a contactor that's not pulling in, you are already going to have divined some information about what's going on well before the contactor. You're going to say, all right, first off, is the thermostat lit up? Okay, well, it's lit up, but it has batteries. All right, well, so maybe that's not so valuable, but the blower's running. All right, well, the blower's running. Then at that point, we know that we have 24 volt power. We've got some 24 volt potential at the outlet or the secondary of the transformer. And we also know that the thermostat's doing something. I mean, the blower's on, so it's feeding through to the G circuit somehow, or the white circuit, or something's bringing the blower on, right? So at that point, we kind of have already decided that we've got 24 volts in this system somewhere. And so then you may go out to the condenser, or you may go to the air handler, and you may check, all right, do I have between Y and C? So I'm already kind of skipping to the switch leg of the thermostat. Now, obviously I'm going to go make sure the thermostat's set to cool and that it's ready to run. But once that's all good and I know that, okay, now my blower's running and I go outside and the contactor's still not pulling in, well, then I'm going to go, like I said, between Y and C at the condenser, which is checking in between the load side of the switch. So line side is red, load side is Y, coming out of the switch, which is the thermostat. Load side of switch, Y, and common, which is my reference point. It's the other side of the circuit. And I'm going to check for 24 volts there, or I'm going to check, even preferably, across the contactor coil itself. And what I'm doing at that point is I'm saying, all right, I'm making not an assumption, but I'm making the decision that this circuit has 24 volts. 24 volts exists because I'm seeing other things operating in the system. And so now I'm going to see, do I have 24 volts applied to this contactor? And so let's just it's a really easy test, because if the contactor's not pulling in and I take my 2 meter leads and I go across that contactor and I've got 24 volts, I make the decision that contactor is not pulling in because the contactor coil is open. Because at that point, if I measure 24 volts there across it, meaning one lead on one side of the coil, which is actually the solenoid that pulls that in, one lead on the other side of that coil, I should have 24 volts there if everything's calling. And if I do have 24 volts there and the contactor's not pulling in, well, it's the fault of the contactor, right? And in most cases, that is going to be correct unless something really odd is going on, or your meter was stuck on lock or something and still reading 24 volts from the previous measurement that you took. If you actually do have 24 volts applied and consistent at that point, that contactor should be pulling in if it's a 24 volt rated contactor. And if it's not, then you can say the contactor is bad. Now, what I would do next is just to prove myself. Once I pull that contactor out, I'm going to put it on the ohm scale, which is resistance, and I'm going to read across the coil of that contactor what I'm expecting to see, because I've made the decision that the contactor has failed. It had 24 volts applied to it, that coil on that contactor solenoid is going to be open, not shorted. Because if it was shorted, it would be blowing the fuse. The fact that it had 24 volts applied and it's doing nothing would mean that it would be open, and when I ohm across it, I expect to see OL, or infinite ohms. I expect to see no path. If all of a sudden I do see a path, well, now I'm going to second guess myself. Okay, that's the reason why I'm doing that test. It's just to reconfirm what it is I already read. And you may say, well, you've done enough already. You've already read the applied voltage. You're right. You're right about that. That is enough of a test, but I'm going to do that anyway. I'm just going to ohm across the coil. Now, here's what I'm not doing. I'm not looking for a specific ohm reading across that coil, because I don't know what ohm reading that coil should be unless I have another one of those exact same contactors that I can compare to. I don't know what the correct ohm reading is. So here's what a lot of technicians do in this case. And again, this gets back to the point of this is, some basic education on how to use a meter, reading resistance and voltage, voltmeter and ohm meter. But what I'm not going to do is I'm not going to read across that thing and say, oh, it's reading 11 ohms. That sounds wrong to me. I'm not going to do that, because at this point, what I've just done is I've said that if what I said was wrong with it, which is an open circuit, I was reading 24 volts applied across it and it wasn't pulling in. The only thing that can cause that is an open circuit. Unless, of course, now, don't get me wrong. If you have 24 volts applied to it and the thing's sitting there going, it's trying to pull in and it's not pulling in, I'm saying the thing's doing nothing, right? It's not functioning as an electromagnet. It is an open circuit. And then I read ohms across it and I'm reading ohms. I'm not going to say, does that seem right? And this is what a lot of technicians do. Another thing they'll do is they'll see a circuit that's blowing a fuse. This is, blown fuses are one of the most commonly misdiagnosed problems. And they'll go and they'll ohm out the contactor coil. They'll just run to the contactor and they'll ohm it out. And they'll say, oh, well, it's ohming out at whatever ohms you come up with. Actually, hold on here. I've got a couple contactors right here, and I've got a meter. There it is. All right, so let's ohm out these contactors. I got a single pole and a 2-pole that I use for demonstration purposes. So let's see. We got the coil on the 2-pole is 10.6 ohms, and the coil on the single pole is 16.4 ohms. And I could say, well, they don't match up. This one with the high ohms is a problem, or the one with the low ohms is a problem, or whatever. Or a lot of technicians say, oh, it's ringing out, right? You hear that? It's ringing out. That ringing out, that means that it's bad. It means the coil's shorted, right? Well, the ringing is just a setting on the meter. And that's just a continuity setting, saying that there is a path, right? And then the setting of that varies from meter to meter, when it rings and when it doesn't ring. And so a lot of technicians will try to divine something by that information, by that ohms information that I just gave you, that resistance reading. And really all I'm looking for when I'm ohming it out is just to see, I thought it was going to be open based on what I measured. And so is it open? And if it's open, then all is good. If it's not open, then I'm going to double check myself. Check yourself before you wreck yourself, as they say. It's always good to double check yourself. But that's the fear that I have in a lot of different tests that technicians do is, why are you doing it? What is the result that you hope to see? In the case of me ohming out the coil, I'm ohming it out because I want to see if it's open, like I had come to the conclusion that it was. So I'm just proving my conclusion. Is it always worthless to ohm out contactor coils? No, it's not always worthless. If you have two of the same contactor coils, or you know what the resistance should be with it in its static state, then that's totally fine. But ohming that out, let's say if I ohmed that out and then I tried to work Ohm's law to tell me what the amperage would be on that coil, it would be totally wrong. I mean, let's just do the math here. So if we take I already forgot what I said. Oh, one of them was 16.4. That's right. All right, so the single pole 16.4. Let me grab my handy dandy calculator here. So 16 actually, no, we got to do this. So we got to take 24 divided by 16.4 equals 1.46 amps. That thing better not draw 1.46 amps. That'd be very high for a contactor to draw. A 5 amp fuse in the thing just as the overcurrent protector. So obviously it's not going to draw 1.46. Once that solenoid is energized and those flux lines start to expand and collapse in there, you're going to have inductive reactance, which is going to add to the resistance, which is going to decrease the amps. And I don't know what it's going to be. I just know that it's not going to be that high. And so I understand the relationships between these things, and I also understand what my limitations are, that I'm not going to use this ohm meter to try to take ohms and tell me whether or not a typical residential contactor, whether the ohms are right. I'm not looking to see if the ohms are right. I'm looking to see if the thing is open or closed. Now, if the thing was had 0.01 ohms or 0.1 ohms, yeah, okay, at that point I would know that that's akin to a short. So in most cases, when I'm using an ohm meter, I'm not really looking to read the ohm value. I'm looking to see, do we have an open circuit, meaning infinite ohms, open line, or do we have a closed circuit, meaning low ohms, right? And maybe in some cases, in some rare cases, I may use a ohm meter or a Megger or a high potentiometer, high pot as it's called, to measure the breakdown of, say, compressor windings or motor windings over time in comparison to ground. So I may do that from time to time, but I'm not really looking so much at the ohm value. The ohm value doesn't matter as much to me. All right, and so that's when it comes to again, this whole point of using a multimeter in a way that's practical. That's what I'm encouraging, is understanding what the limitations are. What are some other limitations? Well, some other limitations are what happens if one of these meter leads is just out just a little bit, and so I'm reading no voltage. Because I just have a loose meter lead, right? And if I'm only going to trust that one reading enough to make a full diagnosis on the unit, I could get a wrong reading. I mean, heck, my meter could be broken. I could have a situation where I'm reading 0 volts. I could have a failed meter. How do I know that? Well, I'm going to use some common sense to assess everything that's going out with the equipment visually. I'm going to look. I'm going to smell. I'm not going to taste. Okay, I don't do any tasting, but I'm going to use my senses first, and I can get a lot of information out of that equipment before I'm just relying on my meter to make that diagnosis, because every tool has some limitations. Some other limitations. I see a lot of guys who will say that they don't have, for example, a short circuit, like in a compressor. They'll say, oh, hey, I ohmed it out. It didn't have a short. Well, it may just be that you didn't have a great connection. You didn't have a great connection on the ground where you were reading to ground or to the suction line. I usually scratch a little spot on the suction line or on the discharge line to read a shorted compressor. But if you don't get a good connection, or you don't get a good connection to the terminal even, I mean, maybe your meter lead slipped a little bit, or there was a little carbon buildup, that can do it. It can also be inside the compressor, because when you don't have that dynamic current, when it's not currently functioning, it's not currently drawing current. Nothing's moving. It's all still in there. And if you think of imagine inside a compressor, for example, or inside of a motor, any type of device that's designed to move. When it's still, there's not going to be as much opportunity for a shorted circuit to bump up against a piece of metal or to short out as it is when that thing is attempting to turn or attempting to move. Once it starts to move, it can very easily short out, where when it's still, it may not actually be actively shorted enough for you to measure with a simple ohm meter. And especially since your ohm meter is powered by a simple 9-volt battery, and it really doesn't do much to boost up that voltage. If you take 2 leads of an ohm meter and you can touch it to your fingers, it's not going to shock you. If you use a megohm meter or a high potentiometer, you'll see that, or high pot. I always call it a high potentiometer. I think my instructor at school used to call it that. But you use something like that, it uses very high voltage, and it's going to be much more likely to read through some oil or through some carbon buildup or whatever, and tell you for certain if you have a short. Now, again, careful here. Don't get the wrong idea. I've done a podcast on compressor diagnosis. I'm not recommending that you use a Megger on every application. They don't work great on scrolls. There's some limitations. It's not always even safe to use them. So I'm not telling you to use it, but what I am telling you, what I'm pointing out, is not that you should use a different tool. I'm pointing out that the tools that you have, the tool in your bag, has limitations. And your multimeter, no tool so much so probably as your multimeter. No tool should you question as much as you question your multimeter, which comes down to simple things like making sure that your probes are in. Whenever I'm going to read a circuit for resistance, I always take the 2 leads and I touch them together to ensure that I have a path. Before I proceed. If I'm reading voltage, I'll often check to an area that I know or assume that I have voltage first, that I have a potential between those 2 different points, just to make sure the meter's working good, and then I'll go to an area that's a more critical test point. So that's being thoughtful about how you use your meter. So now let's talk about actually measuring voltage. So we have the dynamic circuit where everything is operating versus the circuit where it's not. So what's an example of a dynamics measurement of voltage? A really good example would be measuring voltage on a running condensing unit or on a running package unit, whatever. You have a system that's running and you measure voltage on the bottom or on the top of the contactor. So you go between the two legs, between L1 and L2, and you place your meter leads on there. You have it on the volt scale, and you place your meter leads on there, and it reads whatever it reads, 237 volts, say. Well, that tells you something. That tells you that this is the potential that's present even with the circuit under load, which is very useful. You compare that to the voltage when it's not under load, and you can calculate the percentage of voltage drop. And you want to see, with that particular measurement, no more than 3% differential between under load and not under load. Now, that doesn't count under lock rotor amps, because it will jump down more than that when it's under lock rotor when it first starts. But on a running system, you shouldn't see more than 3% on typical application between what it is with no load on it, meaning with the contactor open between L1 and L2 at the bottom of the contactor, and once that contactor is pulled in. That's a dynamic measurement of voltage. And that tells you something, with the system running about that system. Well, what's another one? Well, again, when we're using a voltmeter, we're reading for a difference. We're checking for a difference in charges between 2 points. That's really what a voltmeter is doing. Let's slow down and say that again. When you're using a voltmeter, I say this all the time, but again, you got to get this in your head. When you're using a voltmeter, you're checking for a difference in charges between 2 points. So imagine you're looking at a contactor right now. Just imagine a contactor in your head. We'll make it a single pole contactor, just a simple residential single pole contactor. So on the left side, there's that solid bar. So that's not a contact point. It's not a switch. It's just solid. And on the right, you have that switch, right? So you've got a set of contacts that go in and out, all right? Now, with that contact pulled in, instead of reading across the 2 bottom terminals, which would be L1 and L2, line in, read across the switch. So on the top right, from the top right to the bottom right. With the voltmeter. If you read whatever it is that you do read on that voltmeter, and we're not talking about under a volt, like sometimes you'll read half a volt, and that could just be induced voltage. Like right now, I've got my meter on and I'm reading 0.002 volts just out there in the atmosphere. So, but if whatever you read across those 2 points across that switch, that is the resistance that demonstrates the voltage drop across the switch, which shows that the switch has resistance. So could you do that with a ohm meter. Could you do it with the circuit de-energized and do it with an ohm meter? So I just switched it here with an ohm meter. I'm going to push this one in right here, and it's showing 0.1 ohms, right? I could do that, and that will show me what it's reading with it de-energized. But that doesn't take into account something, like we early talked about the light bulb. On most conductors, I don't know if it may be all conductors, frankly, but on most conductors at least, I know for sure, as you heat them, the resistance increases. And so as you add more resistance, you're also going to increase the voltage drop. So the difference in charges will be greater when they're hot than when they're cold. And so with a set of contact points, that set of contact points is cold right now because it's de-energized. It's not under load, right? But as soon as those contacts pull in, if there's resistance in those contact points, where they're all nasty and gritty and gross, as those contacts heat up, the resistance is going to increase. And as that resistance increases, I'm going to see that as an increased voltage across the switch. And again, this only applies to a dynamic situation, a situation where electrons are moving, there's current, there's amperage, the thing is running, right? I'm going to watch as those contacts heat up that voltage drop increases. And so what I'm going to measure across that switch contact with voltage is going to increase as those contacts heat up. And that can show me that I have contacts that are failing, which in fact is a really good test to do. Now, I'm not going to tell you what the pass-fail is on a set of contacts. I haven't done enough studies of contacts to tell you what a pass-fail is, but I can tell you that it is a good way to tell you if the contacts just look bad or whether or not they actually are creating voltage drop, just measuring across there. Because again, if they create voltage drop, then you will read a difference of potential between the top and bottom of that closed contact that actually has dynamic current going through it. And traditionally, technicians would say, well, the way to do that is to measure across the top and bottom of the contactor. Well, you could do that and compare the two voltages, or you could just read across, and whatever voltage is there shows you a difference in charges, which means voltage drop. I hope you follow what I'm saying here. But just ohming out that contact isn't as effective of a method as reading across it with a voltmeter and checking for that difference in charges, because it doesn't take into account the fact that when those contacts are hot, they're going to have a higher resistance. And when they cool down, the resistance is going to drop again, and also so will the voltage drop. So let's look at another example of this. Another example of this phenomenon and why it's important. So let's say you let's use a really extreme example here. Let's say you took because again, let me step back a second and just get into your head the things that I'm wanting you to know. It doesn't always work the way you think it does on the face of it until you kind of dig in and understand how this works. And so when you have too much confidence in your readings and you start trying to do fancy math and stuff without really understanding how this all works, you can come to really bad conclusions. And trust me, I know I'm the chief of sinners in this area. I've done this many, many times. And usually I end up finding out how wrong I am when I attempt to teach classes about it and I try to do the math and it doesn't add up. So mostly you want to understand how these relationships work so that you can keep from falling into those pitfalls of being overconfident and coming to an incorrect conclusion, because the goal here is to create, have a proper diagnosis, right? And to be able to catch problems with equipment. And the next is to get you using your voltmeter and your ohm meter in a way that is actually useful, and to understand what some of those limitations are. All right, so let's use an example here of let's say you power a condensing unit, the actual high voltage power on a condensing unit with number 18 thermostat wire. All right, you connect number 18 thermostat wire to the bottom of that condensing unit. Now, maybe not the best example because I don't think the compressor would ultimately even try to start, but you know intuitively that if you use vastly undersized wire, that wire is going to get hot, it's going to melt, right? You know that. Undersize a wire, the wire is going to get hot, it's going to melt. And thermostat wire is definitely too small to power a typical condenser of any size. So that's why I'm using this example so somebody doesn't say, well, actually, you could use a number 18 for a blah, blah, blah. No, okay, we're just keep it simple here, okay? So we're going to use a super small wire on a condenser. Now, if you were to take one end of one of those conductors, so let's say you take the red side on one side of the thermostat wire and you go inside 25 feet away and you read on the other side of that red wire. And again, we're powering high voltage condenser here. So understand the scenario here. I'm not talking about just connecting low voltage with number 18. I'm saying we're actually running the compressor on a tiny little wire. Imagine a tiny wire in your head, okay? And we're powering with it. If we were to take an ohm meter with no dynamic current on the circuit, so no work is actually being done, the breaker's off, all that. We were to ohm from one end of that wire to the other end of that 25-foot wire, we would read almost no ohms. when I say almost no ohms, we would read a very low ohm reading. It would show a very good path. So let's say we would read 0.4 ohms on it, or whatever we come up with, all right? And then as soon as you power up that condenser, as soon as you apply load to that, and of course that's significantly more load than that wire's amp capacity can carry, well, that wire is going to start getting flaming, blazing, stinking hot, okay? Now, as that wire heats, the resistance in that wire increases, and also so does the voltage drop across that wire. And it's just going to keep increasing. There's going to be nothing. It's just that wire isn't even close to being able to handle that. Now, as it increases, the resistance is going to increase. And as the resistance increases, the current will actually decrease. And as the current decreases, now that compressor is not going to be able to run. It's not getting enough current to it, right? As the current decreases, it is actually going to be a factor that helps reduce the amount of heat. But eventually, that wire is not designed to handle it, and it's going to melt. It's going to break. So here's something that you have to understand, is that heat and resistance, they are related. And I think in the past, I've actually in a past podcast, I need to go back and listen to it. I think I misunderstood this a little bit, or I explained it in a way that was not good, because we have to think in terms of the entire circuit. So the entire circuit is all the way on a 240 volt circuit. It's from L1 to L2 in the disconnect or in the breaker panel, and that actually goes all the way back to the transformer of the home. But you have these 2 points of differing potential, and they run through and they make this circuit. And it's really the resistance of that entire circuit that dictates the amp draw on that circuit. However, the points of highest resistance are going to be the points that get the hottest. And so when you have a thermostat wire that was not designed for that load, it's going to start getting hot, and the hotter it gets, the higher the resistance, which the hotter it's going to get, and the higher resistance, and it's just going to keep getting hotter and hotter until it eventually melts. And it will have the effect of reducing the current the hotter and hotter it gets. But in the case of this drastically undersized wire, it's going to melt. I mean, eventually it's going to melt. It's going to fuse is the term. Which is actually where we get the term fuse from. It's going to break, right? And we'll even say it. We'll say, well, that wire, the resistance in that wire was too high, right? Well, the resistance in the wire is too high once it gets way too hot. But initially, when you measure the resistance with an ohmmeter, you're going to measure resistance that's low enough that it shouldn't be a problem, right? It's like, well, why would it get hot like that? Why would it do that? Well, because as it gets hotter, the resistance also increases. Those two things are proportional to each other. They're not the inverse. So as it gets hotter, the resistance increases. As the resistance increases, it also gets hotter. So think of it like everything else you learn in air conditioning. As the temperature increases, the pressure increases, So a practical application of this is what I was just talking about with reading across the switch, reading across a switch that's supposed to be closed, or you can visually see that it's closed, and reading the voltage drop across it tells you something about the switch and how well that switch is conducting. That's valuable data that you can get from that. You can see, is there a voltage drop across this switch, right? But here's the thing that I want you to understand. Here's the piece of this, is that when you read something like, we'll say a 24 volt circuit, and you read between red and common, and you say there's 24 volts across these 2 points. Another way of saying that is to say that from the start to the beginning of a circuit, the voltage drop is always 100%. So think about that for a second. It's a weird thing to think, because you're like, well, voltage drop, that's a bad thing. I don't want voltage drop. But the voltage drop in your complete circuit from end to end is always 100% when that circuit is connected and fully energized. You have dynamic current, because the voltage drop is equal to the individual voltage drops of all of the loads in the circuit. That's something, electricians you'll read in a book, right? But all that really means is that the circuit has a particular amount of resistance, whatever it is. Let's say it's 100 ohms, right? And so the voltage drop across that total circuit, 100 ohms, and that includes the wire, that includes the connectors, the switches, the load, everything is 100 ohms. And that's why you read the full applied voltage across the entire circuit. So if you're reading you go to the transformer on the secondary, and you read between the green and the red, and you read 24 volts. Let's say it's 28 volts, whatever it is, right? And you read 28 volts between those 2 points, and then you go down to the actual contactor, and you read right across the coil, so just from one side of the coil to the other, and you read 22 volts. So you read 28 volts, and now you read 22 volts. That's 6 volts of voltage drop that's attributed to the entire rest of the circuit other than the contactor coil itself. And that's proportional to the percentage of the resistance other than the coil itself. That sounded nuts, but let's think about that quickly. So let's do this in easy math. Let's say you have 10 different resistors in a series circuit. So you've got 10 little resistors in a series circuit. That means that each resistor is equal to 10% of the total voltage drop. So if you have 100 ohms, we're going to do this in easy math here. 100 ohms, 10 resistors, 10 ohms each resistor, and let's say the wires have no resistance whatsoever. They're perfect superconductors, okay? So each load has 10 ohms, and it's 100 ohms total, and it's 120 volts, we'll say. I think I said 24, but we'll say 120 volts, okay? That means that the voltage drop across each load, if you were to go to it and you were to apply a voltmeter, across the load, you would see 12 volts at each one. 12 times 10 equals 120, because each one of them represents 1/10 of the total resistance of the circuit, which means that in an electrical circuit, we want all, or almost all, as much as we can get, of the resistance to be in the load that we're controlling. Whenever we have resistance outside of the load that we're controlling, then that results in loss. It results in voltage drop, okay? If you think of an old dimmer switch, like an old school dimmer switch, here's a common misconception. People will say that an old school dimmer switch does not reduce the amperage on a circuit. I actually heard a guy say this. Like, if you take an old school dimmer switch that just adds resistance to the circuit, it adds resistance to the circuit, but the amperage stays the same. Or they'll even say, well, the wattage stays the same. That is totally false. What makes it inefficient is not that the wattage or amperage stays the same, because it doesn't. If you add more resistance to a circuit, you're resisting. Add more resistance, that means that you're decreasing the amperage of that circuit. But what is happening is the loss. You're adding loss, and that loss is going straight into that resistor, which if you remember those old school dial rheostat style dimmers that you would turn, and they would just literally just add resistance. Well, it will functionally dim the light, no problem at all. But what's happening is as you add resistance to that dimmer, you're resulting in a voltage drop to the bulb, and that dimmer is now going to get hot. And so the idea is, well, you actually aren't decreasing the amperage or wattage. Yes, you are. Whenever you add resistance to a circuit, you are decreasing the amperage and the wattage. That is happening. But it's more than the amount that you're decreasing the light. So that means that you're decreasing the light, but you're doing it at a greater expense than you would be if you weren't adding in that additional resistance, which is why modern dimmers, they actually chop the sine wave, so they're actually affecting the sine wave and not just adding additional resistance to the circuit, which is also why you get weird effects sometimes of flickeriness and all kinds of strangeness on light bulbs when you dim them. Anyway, that's a total side note, but that's why we really don't want to add additional resistance. That's why we don't use series circuits. We use almost exclusively parallel circuits. Each load has its own circuit, and we don't want to add in any additional resistance in that circuit. And in diagnosis, the most resistance that you can add to a circuit is infinite resistance, which that's an open circuit. That means that the wire's broke, or the load is severed, or the connector is disconnected. That is infinite ohms. But there's all sorts of kind of intermediary resistances that we can add because of a loose lug in a disconnect or on a breaker, or an improperly sized wire, or a wire that runs over a very long distance. So you have a wire that's just longer than you would want it to be. Now, just an interesting fact, and I talked about this in a previous podcast, is that when you do add a wire that's just too long, so it's the correct size, but you have too much voltage drop because of just the length. So the resistance is the same over the distance of that wire, and the more of it that you add, so let's say the resistance is 0.01 ohms per foot or something. Just made that up, but every additional foot you add, you're adding more ohms, so that heat is still dissipated over the entire length. So you actually are decreasing the temperature of the entire circuit, and it's being carried out over that wire. So that wire's not going to get too hot because it's too long. You're not going to overheat a wire because you make it too long, but you will create more and more voltage drop, which will result in the load, whatever it is that you're attempting to control, having voltage drop to it, and it may not work. Right, so let's say you have a common one would be like a well pump, because you put wells out in the middle of nowhere sometimes, and so you try to bury this long trench, 300 foot of wire, and the pump is a 20 amp pump, and so you think, oh well, I can put number 12 wire on it. Well, not. By the time it gets out there, and it attempts to drive that pump, it's going to be far lower than it should be. So let's say it's a 240 volt appliance, and it's got 20% voltage drop. I'm trying to do math in my head here. I'm stalling. It would be a 48 volt drop in voltage, and so you would have lower voltage than you should to drive the pump potentially. It can cause problems. So you would have to then oversize the wire to make up for the length, but that wire is not going to overheat, because it still would only have 20 amps on it. In fact, adding that additional resistance would actually decrease the total amperage of the circuit, because increased resistance does decrease amperage. But the point at which the resistance exists is where the heat is going to be in that circuit. And so by adding in additional resistance, you are creating voltage drop at that load. Again, you have 100% voltage drop across every completed circuit. So when you have a dynamic circuit where it's actually running, and I read from L1 to L2, power coming into a condensing unit, and I read 248 volts, we'll say. That means that we have 248 volts of voltage drop between those 2 points. There's that is the difference in potential between those 2 points, because the total circuit resistance is measured between those 2 points. The resistance through the compressor, through all those different parallel loads that exist inside of a condensing unit. Now let's think of a different application though. Let's say that the contactor is open, and you read at the bottom of that contactor. Well, you're still going to read the full applied voltage. Well, why is that? Because you don't have any circuit at all, right? Well, right, because you have infinite resistance between those 2 points. There's potential there, so you have 2 points of differing charges, and potential is applied, and there is infinite resistance between those 2 points. No current is moving. There is no dynamic voltage, and so you are going to read between those 2 points the fully applied voltage, because the voltage drop is infinite at that point. Do you understand what I mean by that? It's infinite because the resistance is infinite. When the resistance is infinite, there is technically a circuit, I guess, through the air or whatever you want to make it. But I'm being a little theoretical here at this point, and I've been criticized for doing that. But you have a difference in potential between those 2 points, and you have infinite resistance in between them, and so you're going to read the full applied voltage, which is another way of saying 100% voltage drop. Which is why, let's get down to the nitty-gritty, as they say. Let's say you have a closed single pole contactor. So on the left side, it's a solid pole. There's no switch. And on the right side, there's a switch. And that switch closes, compressor's running, everything's dandy, and those contact points are just shiny, and they're connected, and there's no resistance across them. When you read from top to bottom across that switch, you're going to read almost no voltage or almost no voltage, because there's no resistance. And when there's very little resistance. Again, there's always some resistance, but there's not much resistance. And when there's not much resistance, there's not much voltage drop. And when there's not much voltage drop, you don't measure a difference between those 2 points in that circuit, right? Now, as soon as you open that switch, let's say everything's still intact, it's all perfect working order, but that switch now opens. Now the compressor doesn't run. There's not dynamic current. There's not electrons moving through that circuit. And now you measure across that switch, and what are you going to read? It's a little trick question, but you're going to read the full applied voltage now. Why is that? So a lot of technicians get confused by that. Well, now I'm reading 240 volts again. Well, the reason is because that L1 that's going through the left side pole, and then up through, and then all the way back around, is coming through, and it's hitting the top side of that switch. So again, I'm relying on the fact that you're imagining a contactor in your mind right now. You're looking at it. It's upright. So you've got L1 and L2 coming in the bottom, and then you're going out to your loads, your compressor and your condenser fan out the top of it. And if you're looking on that right side where there's the single contact left side, a single pole contactor, so that's just a solid hunk of brass on the left side. So on that right side, with that switch open, you're going to read 240 volts across it from top to bottom, because it's bleeding through the windings on the other side, windings of the compressor, condenser fan, whatever else, and you still obviously have L2 coming in the bottom on the right. So you're going to read a difference in potential between those 2 points. Because that circuit is open and you have potential on both sides of that switch, you have infinite voltage drop across that switch. It's open. There's an air gap there. Again, it's not infinite because even air has some resistance to it, but you get the point. There's an air gap there, so there's very, very high resistance. So you have near infinite voltage drop across those 2 points, and so you're going to read the full applied voltage between those 2 points, the full difference in charges between those 2 points. As soon as you close it, Now there is almost no resistance. So before there was infinite, now there's almost none when it's closed, and now you don't read any voltage. And so again, you have to know initially, do you have a difference of potential present? It's just like if you don't have a difference in potential, that's like a dead battery. You read across a dead battery, you're not going to read anything. Well, why? Because there's no difference in potential in the first place. So that's what you want to establish in a system diagnosis is, do you have a difference of potential? When you're working on the low voltage side, you're establishing, do I have 24 volts difference of potential? If you don't, then you go back to the transformer. Okay, do I have high voltage coming into the primary? Okay, I do. High voltage coming in the primary, no power coming out of the secondary directly on the transformer. Well, then you've got open windings in a transformer. Then you confirm that with an ohm meter, check for, do I have an open, or is there actually a path and I misdiagnosed something, and maybe I missed a fuse and where I was measuring, or whatever the case may be. So you're always using this combination of establishing, do I have a difference of potential, first off, then do I have an open or closed circuit, meaning does the circuit have a path or not have a path, and you can use a voltmeter for that, and then reconfirm with an ohm meter once you get the part out, and that's generally how I do it. So like let's say I diagnose a transformer, I check the voltage coming into it, the potential, and I've got 240 volts coming into it, and I don't have 24 volts coming out of it directly at the transformer. I'm going to pull it out, and once I get it out, I want to see, is the primary open or is the secondary open? I'm not ohming it out to see what the ohms are. I'm not adding up ohms or doing something like that. I'm just reconfirming what I already diagnosed with the voltmeter. A lot of it's just for my own interest, but I'm not relying on the ohm meter at that point. I already know. I already have a measure of confidence in what I just did. But before I put the new part in, once I pull the old part out, I'm just going to check it real quick, right, with the ohm meter. So anyway, I hope that's been helpful. I could keep going on and on about this and giving you tons of different examples of this, but just think of your voltmeter as a voltage drop tester. Testing for voltage drop between 2 points, and use that as a way to think about this a little bit more. And once you think about it that way, then start to think of things that add resistance to the circuit. Everything that adds resistance to the circuit is a voltage drop generator, and a load is the only thing. So the actual part of the system that's designed to do something, the solenoid in a coil, a compressor, a condenser fan motor. There's all the different parts that actually do something, heat strips, whatever else you can think of. Those are the designed loads. That should be the point of resistance, and so that should be the point at which you get voltage drop. You should get voltage drop across the coil on a contactor. That's why you should see 24 volts applied across it if it's a 24-volt contactor coil, right? Because that's where the voltage drop is designed to be. You're not designed to have voltage drop in other places. So hopefully that'll open your eyes up to a lot of possibilities, a lot of things that can occur in a system, and hopefully show you the benefit of working with the system's own voltage instead of always reaching for the ohm meter. And also recognize, always double check your tools. Don't just trust it on the face of it. Don't be a parts changer. Don't go on what someone else tells you. And if someone tells you the ohm should be X, always question that. Because there are very few cases in this business, other than comparing a thermistor to a table that shows you this is what the resistance will be at a given temperature, or maybe in some high-end compressors, tracking changes in ohms over time for winding degradation. Those are fairly rare circumstances. You're not going to do that a lot. You don't ask the question, what should the ohms be on this contactor, or what should the ohms be on a compressor? Those are not generally helpful things to think of, especially for the average residential, like commercial technician. Instead, think in terms of using your voltmeter as a voltage drop tester, testing for voltage drop. Voltage drop is designed across loads. That's where you should have the voltage drop. Use it to test for potential difference in charges between different points. Use it to confirm things like, confirm that you're not carrying current on neutral. That's another, just as a quick final thought here. That's another good thing you can do is if you check between neutral and ground on an 120 volt appliance, you shouldn't see a difference in charges between neutral and ground because they should be connected, bonded back at the main panel. And if you see a difference in charges between those two, that means that something is awry there. There's a poor connection somewhere along the line. Something's not wired the way it should be, because there should not be a difference in charges between those two points. There's a voltage drop between those 2 points, and there ought not be. So anyway, that's all I want to say for now. Have fun using your voltmeter and your ohm meter to diagnose. So thanks for being part of the HVAC school community. If you haven't gone to our YouTube channel lately, just go to YouTube, type in HVAC school, and you'll find our channel. If you wouldn't mind subscribing to it, that would mean a lot to me. Even if you're not a big YouTuber, it really helps the channel when more people subscribe. Google's like, hey, this channel's good. People want to watch this. We have 2 videos up. One is about replacing a piston metering device with a TXV, with the Danfoss TR6 TXV kit, which I think you'll enjoy. And then another video, we've had a lot of people ask just like, what is the exact outfit you use for pulling vacuums? And so I show that outfit and how amazing it is and how quickly it pulls down. We use the Blue Vac wireless Bluetooth micron gauge and show the app for that, which is pretty cool. So check that out if you're willing to. I would see it as a favor, and I would greatly appreciate it. A lot of you have asked, how you can help. One way that you can help is whenever you share and consume the content, whenever you remember to use it, that's helpful, because what that does is it makes more people aware of what we're doing and ultimately helps the trade, because I think, those of you who have listened for a while, know that we're not perfect here. Not everything is exactly spot on every time, but that we care about the business. The people who I bring onto the podcast, the guys like Jim Bergman and Carter Stanfield, who I'm going to have on here soon, Jack Rise, these are really smart dudes who care about the business, care about seeing it done right, and who care about the future of the trade. And that's what HVAC School is about more than anything else. It's about helping you do the business, day in and day out, actually work with your hands and get it done. But it's also about those who are coming up in the trade, making them better and making them aware of some of these best practices instead of continuously pumping out mediocre technicians who just see it as a way of collecting a paycheck. Because honestly, it's not good for any of us when that happens. So if you can listen, if you can share, if you can subscribe to the YouTube channel, if you can join the email list on hvacrschool.com if you haven't done that yet, those are all very, very helpful things. One thing I want to mention to you too, another thing I want to mention, this is a totally weird out of left field thing, but if you know any designers or engineers, or you work with anybody in the industry, whether they design equipment or design, commercial buildings or duct systems or whatever, there's a really cool software, and these people are not sponsors of the podcast. They're not paying me. They just reached out to me, and they have a really cool business model where it's totally free to use this program. It's called simscale.com, and they can actually take AutoCAD drawings and make simulations to show how air moves or how heat moves within a system, especially if you're designing systems, actually like equipment. I can see how this would be a really, really cool program. Not something that I'm going to really have a lot of use for, so I don't know how much I'm going to be able to talk about it. But if you are in the kind of the design industry and you want to see this great software, this amazing simulation software, you can literally use it for free as long as it's left in the public domain. So if you want it to be like a copywritten work, then you have to pay for a license. But they were telling me about how expensive some of the other simulation products are on the market, and it's just amazing what they're doing for free. And it's really helpful. It's a good thing for the industry because it allows people who previously wouldn't have access to really high-quality simulation modeling now have that access for people who want to create and invent and design things. So if that's you and you have any interest in that, I would recommend that you go to simscale.com. That's simscale.com. Check out what they've got. They've got a little HVAC tab there. You can check on some things there. So again, not a sponsor or anything, but I think it's pretty cool what they're doing. Since it is a Christmas season, so I do need to say Merry Christmas. We're going to maybe should I have like a Christmas special on HVAC School? I don't know. But one thing I did find out recently is that the lead singer of Nickelback, he actually, I don't know if you know Nickelback, rock band, he actually tried out for his Christmas play when he was a kid. But he never made it as a wise man. I think that may be my first and only shot at singing. Yeah, sorry for the Nickelback reference. That's bad on so many different levels. All right, thanks for listening. We will talk to you next time on HVAC School.